Alright, morning. Once again, this is Joel from Aspen Synergy. I'm going to be taking you dynamic and control in Aspen Plus. We want to study the dynamics of a reactor, the CSTR reactor, and the control. We're going to be introducing some control strategy, and we see how it works. Okay, and to get started from the problem statement, we are able to see that ethyl acetate is produced in an esterification reaction between acetic acid and ethyl alcohol, and this is the reaction, and ethyl alcohol is the another name for ethanol. Okay, and we have the steady state parameters. I'm sure you are familiar with how to model a CSTR reactor from our previous tutorial, and these are the kinetic parameters, and I won't be taking much time on the explanation of that. And this is the parameter for the dynamics. And before we get started, I will like to introduce us to some variables. Well, let me see how I can go with that. Okay, let's simulate it first, and I will be from the introductory part. You'll have heard of some variables like PV, process variable, the set point, the manipulated variable, the bias, and the initial value, and the likes. But anyway, during the course of the program, I will still mention some of this, and I will tell you their usage and when you are supposed to use it, so that you'll be flexible when you are using them. Okay, let's get started and start working. For this, I'm going to go to new simulation of the required parameter. We have acetic acid, ethyl alcohol, and ethyl acetate and water. Okay, we've input all the required components. Then we go to methods, method specification. Okay, we are asked to use SYSO, that's Roth's law. Okay, so we click common all, or mix of common, and search for SYSOP, and here is it. Then we are good to go to our simulation environment. Okay, from the simulation environment, we pick the reactor. We have the reactor here, and we click escape. We have the material. Click on this. Why am I using one stream? Just because it's a liquid phase reaction. We need to be having one phase, and I don't want to add vent. Alright, then I can go back to name this as my feed, while this one becomes my products. And I go to the next. I can make use of this next. I like to be using auto run, so that I will know where my problem is at each time. If I input any wrong parameters, it will be calculating the results at each interval. Okay, and I can make use of next, so that I know what to do next. Of course, you know what to do next to define the feed stream. And from the problem statement, with this feed stream is made up of acetic acid, ethyl alcohol, and water. Okay, and the total flow rate is 400 kmol per hour at 75 degrees C and 1.1 atm. 1.1 atm 75, and 400 kmol per hour km/h, and we have this will now be in fraction. Then acetic acid that is coming in, we have acetic acid coming, that's 52.5%. 5.5%. And ethanol coming in, we are, yeah, that's 45%. 0.45. And water coming in 0.25. Okay, and that has completed, and we are good to go. The next thing to do, I have to go and define the block. I can make use of next, we are familiar with it, to take us to the block definition. And from the block, we have that the reactor operates at 70 degrees C and 180 AM. 180 AM. 70 degrees C. 20 degrees. And the valid phase should be liquid only. And we will ask the reactor volume. From here, the reactor volume will be given to be 0.15 meter cube. That's 0.15 meter cubic meter. Okay, this is fully specified, and we go to the reaction. We know how to do that from our steady state evolution. New, and we can add the name, and we are going to be using power law. Okay, I can rename this. Okay, we can leave it like that and continue. Aspen plus rename it. Then we are good to go. The next thing now is to go and define the reaction. Under reaction, this reaction add one that was added to the reactor needs to be defined according to the stoichiometric reaction by adding new, and the component is the acetic acid. Acetic acid is reacting with alcohol, ethanol to produce ethyl acetate and water. The stoichiometric coefficient is that this will be -1, and this one will be 1 and 1. Okay, after all, they are reversible reaction. Okay, so this will be -1. So this will be -1, and the exponent will be 1, because they are both first order based on the first reaction, and this will be 1, this will be 1. The order of reaction does not depend on the exponent of the reaction, does not depend on the products. So we are good to go. Let me save. Okay, to account for the reverse reaction, we create another reaction. You already know that, and that will be in this direction. That's a ethyl acetate reacting with water to form acetic acid and alcohol. Okay, ethyl acetate reacting with water produce acetic acid and ethanol, and by this coefficient will be -1, and the exponent will be 1. Okay, if you watch this one also be 1. Okay, so we're good to go. Then we can input the kinetic parameters, and I'm going to be inputting the kinetic parameters here. For the forward reaction, we have 2 times 10 to the power 8 for A, that's K, and that's 2E8. Okay, and for the activation energy, the 6 times 10 to the power 7, 6E7 as joule per kilometer. Okay, and the basis from here should be molarity. From the pre-exponential data should be molarity. If this is given in partial pressure and pressure units, then the molarity will composition basis will be in partial pressure. Okay, so not to waste time, we go and put this to the molarity, and then we are good to go. Then we'll go to the next reaction, second one, and we are going to have 5 times 10 to the power 7 or 6 times 10 to the power 7. 5 is 7, and then 6 is 7. On this thing, our system has converged. This will be also be joule per kilomole. Joule per kilomole. Joule per kilomole. Okay, and by that, then we are good to go. We are okay with our steady state. Let's check the results, stream results. Has there been any production? Of course, yeah, there has been ethanol reacting with this to form ethyl acetate, and we have seen it that we have production now. Okay, this is our steady state production.